than what will be on the exam. So I want to encourage you that the reason why homework typically is more difficult than quizzes and exams is because you have more time. So you should be taking this at a very deeper level on your own in the trenches, working with reading the textbook, maybe getting some help from a tutor or coming to my office or whatever, and then working through that homework. That's to deepen your knowledge so that when you do take the exam, you understand what you're doing, you can do it a lot quicker. Because again, exams are typically on purpose to put a time stress on you, because the better you know it, the more material you're going to accomplish, okay? And the better you're going to do on it. That's how we test our assessment. So that's just an encouragement to you. Don't get too far behind in this class. The stuff that we're going to talk about today, I'm not going to have you derive Schrödinger's equation, but that'll be super fun. But you're going to have to use Schrödinger's equation and the information, because it's absolutely crucial what we get out of the Schrödinger equation in a practical setting, both for general chemistry, organic chemistry, and biochemistry. Okay, so this is a big day. It's a really important lecture. Some of you know it as 1s2, 2s2, 2p2, but where does that come from and why? So I left off talking about how basically the periodic tables are a way of counting from 100 to 118 electrons in this case. Okay? Electrons move around. That's what we're going to be seeing more and more of. We already saw that that the metals become cations, the anions become, or the nonmetals become anions. They all want to look noble. Well, now what we're going to see is, why is that? Why is there something so special about nobility? All right. Why does everyone want to look noble? And this is explained through the Schrödinger equation, and really the azimuthal and the quantum numbers that we're going to derive this morning or this afternoon. Okay. So please pay attention. Please follow along. This is really important stuff, and it's really, I think it's really kind of some of the more cool stuff that we're gonna work through together. So it's just kind of fun. So Erwin Schrödinger was an Austrian scientist, super brilliant, probably one of the greatest minds of the 20th century. He basically brought together this classical wave and de Broglie's wave particle idea, particle wave idea, and he did it through mathematics. So this is a very theoretical mathematical understanding of where electrons sit. Where does carbon's 6 electrons sit? Where are they? Where are neons 10? Where are sulfurs 16? And we can now begin to answer that question because we have an idea through this idea of quantum, the quantum understanding of matter. Why is it that the chalcogens behave in a similar fashion? Why do the halogens behave in a similar fashion? Why do the nobles behave in a similar fashion? It's because of where their electrons are located in these energy levels. Energy levels are very important. So here's what you need to be thinking through when we talk today and do our worksheet. I'm going to be using some terminology that you need to know. When I say an orbital, what do I mean? When I say a shell, what do I mean? When I say a subshell, what do I mean? When I say an electron, what do I mean? This is all about counting, and you have to memorize what those terms mean, or you're going to be lost. Okay? So when I use those, make sure that we're tracking with the vernacular, because that's very important to be able to speak the language that I'm speaking. Otherwise, we're not using the law of identity, and it's a bunch of gibberish. Okay? So this whole idea of quantum mechanics is, again, like I said, it's a mathematical probability of where the electron is located. Now, I on purpose didn't get into Heisenberg uncertainty principle. Those of you that want to understand that, it's in the chapter. I am not going to hold you accountable for that. That's more of a physics, or when my chemistry majors get to quantum mechanics, they'll have that on their own. So I pulled that stuff out. I'm not going to have you work with the Rydberg equation. You're not going to have to calculate energy level jumps. Again, that's out of the scope of general chemistry. It's there. It's fascinating. It's fun, but we don't need it. Okay? This class does not need it. Dr. Harris's class, that's teaching the engineers, they need it. Okay? Because again, that's where you see it. But typically in a chemistry course, that's more focused to the biology major. It's not as necessary for us to bog down in that deeper math. Okay? We just don't need it. Now, that doesn't mean we're not going to see quantum mechanics and use quantum mechanics. All right? So it's actually kind of cool. Schrödinger proposed this in a paper in 1926. He won the Nobel Prize in Physics in 1933 because of it. Like I said, he's probably one of the greatest minds of the 20th century. He was actually a very kind, very gentle. He loved people. He actually loved to just sit down and have a conversation. He wasn't one of these esoteric or kind of standoffish scientists. He was actually a very kind person and a philanthropist. He really liked to help humanity. He was a really, really wonderful person. But all that to say, another Nobel laureate, Paul Dirac, said of this equation I'm going to show you, the Schrodinger equation. Check this out. This is a very powerful statement. He said the Schrodinger equation that the equation that Schrodinger came up with contains most of physics and what? All of chemistry in one equation. Think that's important? It's probably an important equation for us to understand, okay? Because again, it tells us, it gives us a probability where the electron's found. That's actually that's the aha of the equation. You're not plugging in imaginary numbers and getting an eigenfunction, which is fun. If you take quantum chemistry, you'll get to do that. But for us to use that information becomes really important, okay? And so a lot of people say it's recognized as one of the greatest achievements in 20th century physics. So this is a big deal, all right? So here's the equation. And if you haven't had advanced math with Laplacian operators, and if you haven't had differential equations or calc-free, this is just going to be a bunch of gibberish, all right? And that's okay. Again, this isn't a course in mathematics. But the Laplacian operator here, this, if you see right here, Planck's constant. Remember I told you the quantization of the universe is Planck's constant. So it's Planck's constant, and when we plug in a number, here's what happens with this. We plug in a number, and you can see the Laplacian operator here gives us the coordinates in x, y, z. So those of you that have chemistry before will recognize a couple things. One, you'll recognize this, and this is where we're headed this afternoon. You'll recognize when I draw something like this, or you'll recognize this, or you'll recognize this, okay? Some of you had chemistry before. Oh, that's an s orbital. Oh, that's a p orbital. Oh, that's a d orbital. All of that is in a three-dimensional Cartesian coordinate, right? It's all in an x, y, z plane. And that's what the Laplacian operator actually does. It tells us the location of the electron in three-dimensionality. Right? So what you do with this, and you can see how complex it is for basically a clicker. You can see how complex it gets, and when I show you the actual breakdown of a practical example of it, here's the Schrodinger equation for a one electron atom. One electron atom. And so you can see here, if you go back here, you see V in mathematics terms is potential energy, even though we use slightly different ways to describe it in chemistry, but in physics terms, mathematical terms, this is the potential energy. So notice the potential energy between the electron and nucleus. There's a lot of potential energy in there. How much? Well, this much, all right? It's an eigenfunction. It's an energy state. Again, you don't have to know that, but I just want you to see how beautiful this is. And then we solve it for a certain eigenfunction with its energy, okay? So you can actually solve the location of that one electron atom. If I have a multi-electron atom, now it gets a little more complicated. Why? Well, because now I have the kinetic energy of the electron buzzing around, but now I also, back here, notice, I only have the electron-nucleus interaction. I had the electron buzzing around, I had the electron-nucleus interaction, so I had to solve for those. When I talk about a multi-electron, now all of a sudden there's another potential energy, and that's between the electron-electron interaction. So it gets more complex. Again, it all works out to being the Hamiltonian operator, but I'll save that for when you take quantum. When we go to an actual molecule, here we have, again, all of our kinetic energy of the electron. Here we have potential energy between the electron and the nucleus, but now we have electron, and nucleus. So we add another level of complexity to this equation. You can see how this grows. Now, what does it mean for us? What this equation means for us is we throw in a value, and we get in Cartesian coordinates, and we get a dot. We get a location. We do it again, and we get a location. We do it again, we do it again. And if we do this enough, what begins to emerge is the probability of where the electron is. And if you do it long enough, and if you use a computer to help you do it, because it takes a while to do it, all of a sudden what starts to emerge is a shape. And this is the probability of where the electron is. When we keep doing this, and you can see over time what's happening is I'm actually making this little dumbbell shape that you might know as a p orbital. Okay? So that's what's happening with where we're finding that electron in its location and its probability of where it's housed. So ultimately, we then call that, an orbital. So here you can see the probability of where that electron is located, And again, that's going to be over here in what we call our p block elements. So it's going to have the electron in those p orbitals. Okay? And so we use cartoons. We use a cartoon that looks like this, this, and this, but what we're really saying is that's the probability of finding an electron. Now, here's the crazy thing. This right here is called a node, okay? There is 0 probability of finding an electron in a node. So you have to keep track of nodes. And let me lay on a little secret. If you're in quantum number 1, there are no nodes. If you're in quantum number 2, there is 1 node. If you're in quantum level 3, there are 2 nodes. If you're in quantum level 4, there are 3 nodes. It's basically just -1. Not hard, just have to memorize that. No nodes for n equals 1, 1 node for n equals 2, 2 nodes for n equals 3, 3 nodes for n equals 4, etc., etc., etc. So right here, I know because I have 1 node, I'm at least in energy level 2, okay? Because there's 1 node, and we'll explain that as it goes. Now, those of you that do take quantum physics or quantum chemistry, like I had the privilege of doing in graduate school, you will actually solve these, the Hamiltonian operator for the wave functions, and get the eigenstate or the energy back out. Now that means nothing to pretty much everyone in this class, but I just want to show you that all we're really doing is we're taking a very advanced mathematical approach to the probability of finding an electron and its energy level. That's important, okay? Its energy level. So here we go. We call these things orbitals, molecular orbital. I get to teach, I just got out of teaching advanced organic chemistry last period, and we're talking about frontier molecular orbital theory. We're actually talking about using this at a practical level to understand complex reactions like Diels-Alders and Wittigs and some really fun organic chemistry. But what we're working with are these things called orbitals. This will never change. An orbital can only hold 2 electrons. That is it. So you have to memorize that. Orbitals only hold 2 electrons. Whether we're talking about an atomic orbital or a molecular orbital. When we get into molecular orbital theory in this class, you're going to see this is going to come right back. Orbitals hold 2 electrons, okay? So we call those, again, those wave functions, that's what we practically call an orbital. Holds 2 electrons, all right? Each orbital then describes the spatial distribution of the electron density. That's exactly what's happening here. Okay, this is a p orbital. There are 2 electrons in there, all right? So with that, they tell us where the electrons are located, all right? So Schrodinger's equation for us requires 3 quantum numbers. There's a total of 4, but Schrodinger's equation only requires 3. Those are the principal quantum number n. It's going to be it's just going to be an integer, 1, 2, 3, 4, 5, or 6. Okay, typically we go to 5. Number 2, the azimuthal quantum number. That describes the shape. That's the one that gives us the S, P, D, or F. If you had this at some level. Okay, the third one is the m sub L, or we call that the magnetic quantum number. That describes the 3-dimensionality. And again, I'm going to review all this and show you that we're going to work this together. I think it's actually really neat stuff, to be honest with you. Okay, so N, L, M sub L. There you go. Those are the 3. Then there's M sub S, but we'll get into that when we get to Pauli's exclusion principle. But the 3 that requires for Schrodinger's equation is principal quantum number, that's azimuthal quantum number, and the magnetic quantum number. N, L, M sub L. We're tracking? Okay. So, with that, are quantum numbers. Quantum numbers, again, are these energy, if you will, levels, so to speak. The energy level of the electron's location. Okay? So each quantum number is going to be an integer, 1, 2, 3, 4, 5. All right, so quantum number 1, the principal quantum number 1 tells me the energy, all right, where it resides. They are values of equal to and greater than 1, all right? So what happens with this is we have n equals 1, n equals 2, n equals 3, n equals 4, n equals going up 5. Now, it is exponential. All right, so the gap between 1 and 2 is larger than the gap between 2 and 3. So I've kind of simulated that here. But my principal quantum number is 1, 2, 3, or 4, and 5. I can go up to 5 if I'm down here with my lanthanides and actinides, but typically in most case settings, we'll stop at 4. Okay? So with that, those are my energies. So N is real easy. 1, 2, 3, 4, or 5. All right? That's it. That's all you get. Now, my azimuthal, the one that tells me the shape, which is a really important one. All right, and again, this is the energy level that goes this way. All right? So my azimuthal defines the shape. What are its allowed values? Well, notice, they're going to be range from 0 to n minus 1. It's not complicated. It's going to be 0 or n minus 1. So 0 or n minus 1. 0 or n minus 1. Okay? So I'm going to go ahead and start working. I'm going to do 1 through, I'll do 1 through 4. So let's go n equals 2, n equals 3, and n equals 4. Okay? So with this, what are my values of n equals 1? Well, really, I have 0. Okay? I can have, here, I can have 0, or I can have -1. Well, hold on, I'm gonna do this a little bit differently because I really don't want to get you super confused right now. So actually, I'm gonna come back to that because I'm starting to already go to the next one, and I don't want to do that on purpose. Okay. So these values, notice, are from 0, 0, or n minus 1. So I'm gonna have 0 here. That's all I get. Here I'm gonna have 0 and 1. Does that make sense? Because 2 minus 1 is 1. Here I'm going to have 0, 1, and 2. Make sense? And here I'm going to have 0, 1, 2, and 3. Are we all tracking? Okay. So with that, when it's 0, over here, 0 equals an s orbital. 1 equals a p orbital. 2 equals what we call a d orbital, and 3 equals an f orbital. Okay? And those are just conventions, SPs, Ds, and Fs. So it's a way that we take the quantum number that comes from the Schrodinger equation, we make it more practical. Because I don't really want to know that carbon has a 0 at the energy of n equals 1 and a 0 at n equals n equals 2 and a 1 at n equals 2. I want to know it's an S, and a p orbital. So that's how we actually use that information. But that's what's going on here. It's the actual solution to the Schrodinger equation. Okay? So stay with me on this. All right. So again, we designated S, P, D, and F. So 0 is S, 1 is P, 2 is D, F is 3. Okay? Next one is the important one. So n equals 1, n equals 2, n equals 3, n equals 4. Of that, I have all these possibilities. Now, S, P, D, and F. Okay. The magnetic one now tells me my three-dimensionality of the actual orbital. Okay, now this is important. These have values from -L through 0 to L. So that's when I started to do this up here, and I didn't want to do that quite yet. So notice, I have a 1 s orbital. Here, I have a 2 s orbital, and I'm going to have 3 p orbitals. Why? Well, notice this. This tells me that I'm going to have spatiality or dimensionality from -L, which in this case is 1. So it's going to be -L. So here's -L. Here's 0. Here's +L. Okay? Tracking? Up here and here, I just have 0. Right? I just have 0. So here, I'm going to have 0. Whoops, not there. Which is going to be an s orbital. I'm going to have 3 p orbitals. But because I'm n equals 3, remember, I have 0, 1, And here I can have 2 because it's n minus 1. So how many choices do I have? Well, negative L, so negative 2. So negative 2, negative 1, 0, 1, 2. Oh, I have 5, and these are what we call d orbitals. So this is going to be negative 1, 0, this is 0, negative, or positive 1, negative 2, negative 1, 0, 1, and 2. Are we tracking? This is my principal quantum number here. These are sub-shells. Sub-shell. The entire shell is my n equals 3, n equals 2, n equals 1. Okay? So, principal quantum number as Muthel, 0, 0, 1, 0, 1, 2, right? How many can each hold? Negative L to L. So 0, that's it. If it's 0, it's still 0. If it's 1, then it's minus 1, 0, positive 1. You see this? If it's 2 for d orbital's 2, it's negative 2, negative 1, 0, 1, 2, because L is 2. So what's 4 going to be? Yeah, exactly. It's going to be, so I'm going to have a 0, negative 1, negative 1, negative 1, negative 2, negative 1, 0, positive 1, positive 2. But now, see, I've got a 0, I've got a 1, I've got a 2, and I've got a 3. So now it's going to be negative 3, negative 2, negative 1, 0, 1, 2, 3. Oh, that's cool. Check this out. Over here, where I have what we call our s block elements, I only have 2 electrons. Oh, 2 electrons. Probably these have electrons in s orbitals. They do. Well, then check this out. Over here, I have the p block elements. How many electrons can they hold? Well, 1, 2, 3, 4, 5, 6. Oh, that's kind of cool. Each orbital holds how many electrons? So this can hold 1, 2, 3, 4, 5, 6. How many electrons can a d hold? 10. 2, 4, 6, 8, 10. Huh, that's interesting. It's interesting that the transition levels right here have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Fascinating. Maybe their valence electrons are in d orbitals, and they all have that. What are we going to guess down here for the lanthanides and the actinides? Probably like 14. Why? Because I have 2, 4, 6, 8, 10, 12, 14. And that's the way we have the S block elements, the P block elements, the D block elements, and the F block elements. And it all comes from the theory of Schrodinger's equation. Okay? And it begins to make sense then. Here's what's happening. If I have a little electron up in an s orbital, I'm in a higher energy state. If I lose it, I jump down and I look normal. It's all energy driven. Okay, that's why we just came out of thermodynamics. It's energy driven. So with that, you can see now that we have this, and I'm going to redraw this. I'm going to redraw this for you. I just wanted to show you energy. Here's what it actually then looks like. Here's how we think of this. So we think of this as my energy level. And I'm going to do boxes. I like lines because that's what I teach the advanced classes with, but boxes are fine as well. So my n equals 1 has a box that can, an orbital, we'll call it a box, an orbital that can hold 2 electrons. N equals 2 has a box and 3 boxes. So it can hold 2, 4, 6, 8 in the n equals 2 energy level. N equals 3 then has this. Oh, and then it also has 5 out here. Okay? And then when I go to n equals 4, each of those boxes is a molecular orbital. Each of those can hold 2 electrons. So here's what happens. When I count from 1 to 10, all I'm doing is counting electrons. And notice how I count them. 1, there's an electron. That's hydrogen. Oh, 2, that's helium. Oh, wait a minute. Helium's noble. Huh. That's kind of weird. It doesn't like to gain or lose electrons because n equals 1 is full. Okay? Here's lithium. Here's beryllium. Here's boron. Here's the greatest atom of all time, carbon. Here's nitrogen. Here's oxygen. Here's fluorine. And here's neon. Oh, wait a minute. Neon's full. Oh, doesn't want to gain or lose electrons. Why? Because n equals 2 is full. The energy level's full. And then here comes poor little sodium. I got to stick an electron up there. No wonder sodium wants to get rid of it. If it gets rid of it, its n equals 2 is full. And you see how this builds. Okay? But I have to stop there because we have to have the Aufbau diagram because it gets complicated after this. All right? So are we all tracking us to what's going on here by counting electrons? Now what you can see with this is these are the s orbitals. These are the p orbitals. These are the d orbitals, and these are the f orbitals. I started this whole thing with the whole concept of nodes. This one has no nodes. This level has 2 nodes. Or excuse me, 1 node. This level has 2 nodes, and this level has 3 nodes. So we have to explain that. What do we mean by that? And then we're going to make this practical. Okay? So there's our values from m sub l. Again, so we can have a 3s, we can have a 2s, we can have a 1s, we can have a 2p, we can have a 3s, we can have a 3p, we can have a 4s, a 4p, a 4s, a d, and a 4f. Okay? So when you memorize your 1s2, 2s2, what that 1 is your energy level, your principal quantum number. 1s2 tells me that I have 2 electrons and energy equals 1 quantum level here. Okay? So your overall diagram looks like this. Now, this one comes out of your book. I don't like it. Anybody tell me why I don't like it? Is it different than the one I have on the board? Yeah. Why? How? What is it? It's been flipped. Hasn't it? Isn't this the 1s and the 2s and the 3s and the 4s? And the reason why I don't like that, that's not the way you think about it. Energy doesn't go down, it always goes up. Okay? So we're going up in energy. This here is energy. Energy is going up. That has energy going down. I just don't like that. It's not convention. So for some reason, the author just flipped that, inverted it. It doesn't make any sense. Now, here's really what we're looking at. So what we're looking at here is, here's my n. Here's my possible values of the azimuthal. Here is my m sub l, okay, or my magnetic. Oh, excuse me, here, magnetic. So remember, m sub l has values from negative L through 0 to positive L. So we have 0, 0, 0, 0, 0. The 2s is also 0. Ah, here's my 2p with 1, 0, negative 1. Here's my 1, or my n equals 3. There's my s orbital. Here's my p orbitals. Here's my d orbitals. Oh, here's my s orbital, p orbital, d orbital, f orbitals. Notice total numbers of electrons that can go in those orbitals. It's going to be twice that number. Okay? So this is where we talk about number of orbitals in subshells. In subshell. Notice this has 3 orbitals, right? And this is what I'm going to describe next with some graphics. These are really cool to see these actually play out. So here's our s orbitals, right? Here's our 1s, right there. Here's our 2s, right there. Here's our 3s, right there. Here's our 4s, down here. It's off the graph, okay? But I said that they're different, and they're different by the number of nodes that they have. So what do I mean by a node? A node is a 0 probability of finding an electron in that location. 0 probability, all right? So the 1s doesn't have a node, so it's going to be found somewhere in that 1s sphere. But this one's different than that one, and it has a node. The question is, how does it have a node? Where is the node? Well, it's like an onion, all right? And if you look at it, it's right here, okay? And it's right there. It's a 0 probability of finding the electron. And when you go to the 3s, so this is the 1s, no nodes. This is the 2s, has one node right there. See it? And here's the 3s, right there, has 2 nodes, 1, 2. And what do you think the 4 nodes? It's going to be the same thing. There's a 0 probability of finding it there, which is weird. Because how does it cross over that and never land there? Kind of one of those weird things. It's just there. It's quantum. Okay, welcome to it. So those are the nodes. So that's how we see that with the s orbitals. All right. When we look at p orbitals, it's going to be the same thing. Here's your p orbitals. All right. P orbitals now. Notice this p orbital is different than this p orbital, which is different than this p orbital, only in geometry, or only in three-dimensionality. Right. So you're going to have one that's on the z plane of p. You're going to have one that's on the x plane of z, and you're going to have one that's on the y plane of z. Okay? And again, each of these little dumbbells holds 2 electrons. So out here buzzing around in our Schrodinger equation, over time, is the electron density. And we just make that a little dumbbell. Cool? Now you might be thinking, oh, you're right. It has 1 node. So the 2p has 1 node. The 2s has 1 node. So what do you think the 3s has? No, excuse me, the 3s. 2 nodes. How many nodes does the 2p have? 2 nodes. How many does the d orbital have? 2 nodes. You get the pattern here? So this has to have 3, this has 3, 3, and 3. So the 2p naturally has a node because it's a dumbbell. So we think about that, and what we're saying is there's a node there. When we go up further, notice, how do I have 2 nodes with the 3p? I'm going to go back. How do I have, so this is a sphere, looks like that. This is a sphere. This is a sphere that looks like that. This is a dumbbell, okay? What does this one look like? It has to have how many nodes? 2. So this one is a p orbital, but it looks like that. It's like a piece of candy that's been twisted at both ends, okay? Has 2 nodes there and there. What's the d orbital look like? Well, the d orbital has to have 2 nodes, so that's why it looks like that. It has a node there, and a node there. It has 2 nodes. Okay? So again, you're seeing the fact that these orbitals that you might have messed with in s orbitals, p orbitals, and d orbitals all really do make sense when we look at it through the quantum lens or the Schrodinger equation. Okay? So here's my s orbital, here's my p orbitals, and here's the d orbitals. Now, it's that middle one on the d orbital, what we call the d sub 0, is really cool, the mathematical solution as to why it's a donut with a dumbbell between it. But I'm not going to get into why. My professor in grad school really loved, he was fascinated with that orbital, so we all had to solve the equation as to why it looked like a donut and a dumbbell. And it only took like 5 pages of math, so it wasn't that bad. But still, it's not one of those that's really obvious. But the rest of these are, right? Node, node. Node, 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 node. Okay? Yeah. There's the glorious D. And there's 5 of them. 1, 2, 3, 4, 5. Huh. 1, 2, 3, 4, 5. Kind of cool. Oh, there's the f orbitals. Aren't they cool? And so the f orbitals up here should have 3 nodes. Naturally, they do. 1, 2, and 3. All of them have 3 nodes. Isn't that cool? Yeah, so that's the probability distribution of where the electron's found. So S's are spheres, dumbbells, double dumbbells, and then F's are triple dumbbells, okay? And there you go. So with that, with the orbital diagrams, again, that's why the periodic table starts to make sense, because we have our S block elements here. These have electrons in S blocks. These have electrons in D blocks. These have electrons in P blocks. These have electrons in F blocks. So they're all going to have a very similar chemistry and where those electrons are moving around. Kind of cool? Any questions on that? No? You got it? Okay, you got it. Let's make it more complicated. So what happens with this is like something like the F orbital. How do I actually put the electrons into these orbitals? Well, here's the thing. There's a couple different rules. We've got Hund's rule, Pauli's rule, and thing. something to do with energy that we have to flush out. All right, so again, we're going to combine these later down the road. This is kind of a fun, you can see that this is a solution to this is a mathematical calculation to where the electron's found. What is this one? This one is let's see, we're going to be in a n equals 6, azimuthal of 4, m sub l equals 1, and it looks like that. That's where the two electrons are found somewhere in those orbitals. Okay, that's what it actually looks like when it starts to mix. Kind of cool, kind of fun. Again, you can do these on computers. Here's another one. If you have actually 2 electrons mixing, there's their solution. There's their probability of being found is somewhere in those there. And again, that's what we think electrons are. It's where we think all the electrons are buzzing around out here. And they are in some orbital somewhere that looks something like that. A couple more, just kind of fun. You can see some of these are actually really kind of cool. But these are the interactions of the eigenstates. And again, there's electrons found in there to form a bond. Kind of weird, isn't it? Kind of cool? Yeah, kind of fun. All right, so number 1 rule before we start to dig in, is the Pauli exclusion principle. Pauli exclusion principle says no two electrons can have the same 4 sets of mathematical solution. So what we do with that is we have one more number, and it's called the spin, basically. No 2 electrons in the same atom can have exactly the same energy. Okay, that was the Pauli exclusion principle. Now I have already done that up here, but I didn't tell you that's what I did. Okay, one little electron is up, and one little electron is down. And they cannot have the same spin. So you can't pair spin 2 electrons, they have to be opposite. Okay, so that's Pauli's exclusion principle. And so basically what happens is we get an electron spinning up and we get an electron spinning down. And by the way, that's what we capitalize on when we're working with nuclear magnetic resonance spectroscopy. We're actually dealing with the spin of the nucleus. Okay, it's actually super cool to see that, and then its interplay with the electrons, but we'll save that for a little bit more complication down the road. Okay, so we call this the m sub s, or the m sub spin, and it's an up or down. That's all it is. And that's why here on my diagram, I have a little electron up and a little electron down. Okay, so in this molecular orbital, these 2 electrons cannot have the same 4 quantum numbers, or same 3 quantum numbers and the m sub s. Okay, all right. So again, they have this value of half spin, half up, or half down. All right. Now, here's what we are talking about so far. We're getting closer. We have a 4p5. Yes?
What were the 2 spin numbers?
Negative half and positive half. And that's the sort. But for now, we're going to stick with that. Okay, so this is where we're headed. To be able to take the electrons, let's say I had an electron with, I gave you something like bromine. I said, where are bromine's electrons? And you can tell me exactly where they are. All right, and that's where we're headed. So with this, the big number up front tells me my principal quantum number. That's what that is. That's n equals 4. So it tells me I'm up here. Okay? The p tells me my azimuthal is 1. We just call it p. And it's probably easier designation than 415, so they go 4p5. 5 then tells me, the superscript tells me how many electrons are in here. Okay? So it's a 4p, and there are 5 electrons. Okay? So that's what that signifies, 4p5. All right? Now, each box then holds 2 electrons. Okay? That's what I've been doing the whole time. So lithium is a 1s2, 2s1. So lithium is a 1s2, 2s1. I'm on lithium. All right. Now, watch what happens here. So I started doing something, so I'm going to go back and fill this. Okay, so we fill this. So we fill this way. We fill it. Okay, so there's beryllium right there. When I go to boron, no problem. I'm going over. So now I have 5 electrons. So I'm 1, 2, 3, 4, 5. But here's what happens. When I go to 6 electrons, when I go to carbon, I have 2 choices. I could either put it here, or I could put it here. And this is what's called Hund's rule. Hund's rule says it's lower in energy to have the electron in a new orbital than putting it, cramming it in the same orbital. So that's why carbon looks like that, not paired up here. So when I go to carbon and then I go to nitrogen, nitrogen could put one here, 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 but it chooses to put one in the open orbital. But now when I come over to oxygen, oxygen says, okay, now I'm stuck. I have to put one in a degenerate orbital, so I'm just going to put it there. And so fluorine puts it in there, and then neon puts it in there and fills it up. Okay? So Hund's rule says, go ahead and fill the orbitals before you spin pair the electrons, because it's lower in energy to put them in new orbitals than it is to spin pair. Okay? We're almost there. Now, here's what happens with this diagram, and where it gets a little bit, and it's not tricky, you just have to know it, and so I'll show you how it works. Once we put an electron in this, once we put an electron in the n equals 1, once we do this, that's all theoretical. That's all theoretical from the Schrodinger equation. But when I do this, the whole picture changes. Because now that electron is interacting with the other orbitals. So I have to know how that works. This is what's called the Aufbau diagram. It's not hard, but you have to know this. And here's what you do. You start with 1s, go to 2s, 3s, 4s, 5s, and 6s. That wasn't very hard, was it? Okay. Now I go to 2p, 3p, 4p, 5p, 6p. That wasn't very hard, was it? Now I go to 3d. I go to 3d, 4d, 5d, 6d. Okay. Again, that wasn't very hard at all. Now I'm going to go to 4f and 5f. There's no 6f. Okay. And you could go to 5g if you want. That's all theoretical. That's what they're trying to get to when we are trying to get past 118. When we go to 118, we're going to be in the g orbitals, but that's all theoretical, so we're not there yet. So that's as far as we need to go. So when you're filling electron locations, watch what happens. Again, not tricky. If you can do what I just did, you just drew the Aufbau diagram. But here's how it's filled. It's filled in this direction. 1s first, 2s next, 2p. Okay, everything. Remember, I stopped at sodium on purpose. Everything's fine right there. I'm going to go to the 1s, then I'm going to fill the 2s, then I'm going to fill the 2p, I'm going to come back to the 3s. But watch what happens now. I go from the 3p to the 4s. So the 4s gets filled before the 3d does. Then I come back to the 3d and go to the 4p to the 4s. So this is what we call the Aufbau diagram, and this is the direction, yes, you can go to 7s, in which the electrons are filled. And that's all you need to know. Now you're ready to roll. How fun is that? So let's say we do carbon. Carbon has 6 electrons. So if I do carbon, 6 electrons, where are they? Well, 2, 3, 4, 5, 6. So carbon's going to be 1s2, 2s2, 2p2. That's pretty cool. There's carbon's electrons. All right? But what if I do something like chlorine with 17? Well, so chlorine, 17, I'm going to fill 1s2, 2s2, 2p6. And Aufbau tells me now go next to 3s, fine. So 3s2, and now I come back down to 3p, 3p, and I probably need to start counting. So 2, 4, 6 is 2, 4 is 10, 11, 12, I need 14, so I'm a 3p. And that should equal 17 electrons. So 1, 2, 3, 4, 10, 17, we're there. And so this is how the electrons actually get filled and where they are. Now here's what's really cool. You can have your valence electrons explained through nobility. Because notice chlorine at 17, if you go back to 10, 10's noble, so chlorines, these are all noble, so sometimes what we actually do is we abbreviate that. So I don't need to draw those out. I can say that I know that it's the configuration of neon plus a 3s2, 3p5 or something in that regard, okay? And so we actually do see chlorine making up to 7 bonds, which is kind of fun. We'll get into that when we get into Vesper. But this is where all the electron comes from. But what are we talking about? In this, you're seeing Schrodinger's equation. You're seeing quantum chemistry. This is my quantum number. This is the azimuthal, okay? This tells me how many electrons are in there, all right? So, and I can hold up to 6 because again, I have 3 planes on which those p orbitals can reside. Questions on that? I think that's pretty cool. I think building on Schrodinger's equation to understand where the electrons are really gains a lot of knowledge as to why the periodic table behaves and why it interacts, why these atoms interact the way they do. Okay? Good? No questions? Got it? Okay, why don't you try one, and then we'll stop, and then we'll do a workday Wednesday. Why don't you tell me where? Why don't we go ahead and let's do a fun one. Do silver. Give me the electron configuration for silver, not the short-handed one, the full one. So silver is Ag. It's number 47 right there. I know. So do 47. Let's see what we get. 47 electrons. Well, at least I didn't make you do Seaborgium. That'd be kind of fun. Yes. Oh, I'll do it. Yeah, I'll do it. Okay, guys, we're ready to do it? Okay, so we got to go 47. So we got to count. So let's go 1s, 2, 2s, 2, 2p, 6, 3s, 2. Where are we at next? I'll follow that. Who's next? After 3s? 3p, 6. Then from 3p we go to 4s2, and we come back down to 3d. How many? 10, good. So 3D now up to 4P, 6, and then 5S, 2, and where are we? Well, let's stop and make sure we're not too far along. 10, 11, 12, 18, 19, 20, 36, 38, got a little bit forward to go, no, so we're at 38 here. So 5S, so now we're going to go to 4D, 10, so now we're at 48. Oh, hey, we can go back one. So we're at 49. There you go. Isn't that kind of cool? Is that not, did I miscount?
No. I'm just tired. I didn't like this.
You didn't like this the first time around?
No, I don't like it.
It's really practical. Wait till we start mixing them and get into hybrid states. It's really fun.
Oh, no.
Okay, on Wednesday, I'm going to finish the chapter. I just have a couple, we'll talk about anomalies. And then we're going to do an all-day workshop. working on it. Okay, get ready for our exam on Friday, and I'll explain what's be on the exam on Friday, okay? What's that? No quiz on Wednesday. I'm not gonna do that to you. We're gonna make it a work day.